It's my pleasure also to have a chance to present the work on the topic planning for superhuman autonomous vehicle, which I did mostly through my PhD research. So in Virtual Vehicle Research Center and Technical University of Graz, where I did my PhD. So during this tutorial, please feel free to stop me at any time. So raise your hand or write in the chat, and Henrike, can you then just forward us the questions, or just raise the hand and you can speak freely later to ask any questions. Stop me. The goal is that you learn the most. So I will try to give you, actually, I never did this long talk on research work which I did, but so I added a lot of theoretical background, so you will have a theoretical basis to understand better the practical part, which is quite applied. You will see later that we also tried some of these things on a real vehicle. We tested with human participants and so on, so it's very practical work. But on the other hand, also it stems from a really sound theoretical background, and also the theoretical background I will shortly introduce to you. So I hope that through this tutorial, more or less, you will be able to comprehend all of the presented work quite nicely, and that you can understand what are the contributions, let's say. So the theoretical work is more or less very thorough, and actually I don't have much time to go very much into details, but I hope it will be enough that you understand it well. So to start, the outline of this tutorial looks like this. So I will just give you the introduction. This would be the motivation. So giving the introduction to the project I did, autonomous vehicles in general, and also autonomous vehicle control architecture, which is and the focus which is shown here. Then we will go more into theoretical foundations. So we will touch the motion planning problem, which is usually a problem from an approach of robotics. And also through the tutorial, I would like to present you different perspectives, let's say, to the project. So maybe it will give you some inspiration solving your PhD problem or something, and give you some different ideas how to solve your problems. The other method is dynamic programming. So this is the approach from optimal control. Mainly in this case, it is discretized problem and solving it as a dynamic programming algorithm. And then the next one is A-star search, which is a path planning algorithm, which is used also for solving the same problem. So through the tutorial, you will see how I employ different of these algorithms and methods to solve more or less the problem. Then after the theoretical foundations, we will go for a break. So we will have maybe 10 minutes, 15 minutes break. We will decide, and then we go for a practical part where we go into applications which were covered by my PhD work. So mainly different autonomous vehicle use cases. We go into more details into what I call superhuman autonomous vehicle. Then we will show the energy efficient driving use case, automated driving use case, and in urban traffic, and then performance driving, and maybe also touch a bit of parking use case. Through all of these use cases, we will see how we do different models. So modeling of vehicle dynamics appropriate for the given use case. So usually we can always have a very good model, but then if it's too complex, algorithm becomes slow. So we will see how we have a different gradings or different levels of vehicle model fidelity, and how we use them and interplay them with algorithms. then very much related to vehicle modeling, we will also see how we form the search space. So most of these algorithms are search algorithms in some sense. So how we formulate search space, then how we formulate different obstacles or constraints on our motion and so on, and our planning approach and validation. And then finally, we will look into some ideas, what are the open issues and outlook for this problem. So do we have any questions so far? If not, then we can start. So most of this work, as I told you earlier, was done during my PhD studies, which was done within ITEAM project. So it is Marie Curie project coordinated by Technical University of Ilmenau and with other colleagues, and it was also very nice platform for me to be able to research. I also did some parts of this research together with Volvo. We tested in Sweden some parts of these algorithms. Then on other hand, I had the opportunity to go to TU Delft before for a research visit to University of Sarajevo and so on. So to give you introduction, what's happening and in general in this intelligent agents, let's say the scene. So I will just give you a short trend line. So we have maybe the three major topics here. So one is artificial intelligence. So we have this is a hardcore computer science topic, right? So we have a goal to achieve general artificial intelligence, and the goal is to achieve, in a sense, superhuman capabilities. On the other hand, we have a robotics, which is kind of an embodiment of artificial intelligence. So this is kind of artificial intelligence in general, operating in real world and having some hardware, having some capabilities to do some meaningful work in except some software computations and software work. And the third one is automotive, which is quite advanced field, which is kind of, especially with autonomous driving, one of the specialties or specializations of robotics, let's say. So mobile robots operating in let's say some complex world, but also regulated and having some rules. So if we look into some milestones in the artificial intelligence, we see that we have also some initial works related to checkers games. So from Arthur Samuel in 1959 or something. So he developed some algorithms for playing checker games. In robotics, a little bit afterwards. So robotics usually was always a bit of behind of artificial intelligence because there were also many other problems existing except only control or the brain, let's say, of the robot, and also usually having some limited computation power because it has to be on a robot and so on. So it was usually a bit of lagging after the artificial intelligence. The shaky robot was the more or less the first intelligent robot, which had a path planning algorithms, and we will see later A*, which was employed, and robot was able in some kind of intelligent manner decide where to go in the free space around it. On the other hand, in automotive, there was a big Prometheus project. This was in I think end of 80s starting, so very huge European Union project funded and focused on getting autonomous driving, and we will see later there were some quite nice achievements. Then later we had some kind of the second era. Artificial intelligence, also IBM's Deep Blue managed to beat Garry Kasparov and world champion at that time. So it was a quite big milestone. On the other hand, in robotics, the robot motion planning algorithms became much more efficient, and there was a RRT algorithm going out from Steve Lavelle and so on. So robots were getting much more intelligent. And also in the automotive, there was a DARPA Urban Challenge, which some kind of kicked off this modern era of autonomous driving. And mostly people, when they go to history of autonomous driving, they just go into this part, but there was also history much before. And then the recent era in artificial intelligence, with ImageNet or AlphaGo, which is probably famous, known to many of you, and also followed by robotics, which is robots which are able to learn from scratch and learn the tasks in reinforcement learning manner, became very presented. And in automotive, you already have some kind of companies starting and kicking off with Waymo, Uber, now also many German OEMs and so on. So they are already offering some very high level capabilities of autonomous driving. And also, more or less, the goal is that we have a really in this work, like to pass after this, to have a superhuman autonomous vehicle in all of the driving aspects, and we will see later how these other works are limited. So if we go back to history, the actually also the one of the first mentioned or the documented mentioning of autonomous vehicles and the traffic and automated traffic and so on was in 1939. This was the exhibition in US, Futurama, and it showed the cities with autonomous traffic already in 1930s. Then there was also some practical work already in 50s with GM and Radio Corporation of America, and they had some kind of magnets embedded into road, and the vehicle driving was able to detect magnets and somehow to steer the vehicle and to follow this road, and also to, in some sense, keep distance to vehicle in front. But this was just some experimental work. In 60s, also work on mobile robots started. So this is a Stanford Cart predecessor, in some sense, also at the same time as Shaky robot. So this was the plan to be a lunar explorer or something, just to emulate it, and it was actually very slow. And as I mentioned, also Prometheus project, this was in 80s, already a serious work in Europe and having the full vehicle, large-scale vehicle running on a street. So I will play the video now.
The most striking successes have been achieved in autonomous road vehicle guidance. The test vehicle, VAMORS, seen here, has been in operation since 1986. This period was preceded by 8 years of preparatory developments, with different types of simulation culminating in the real-time simulation loop. Based on data fusion from various sensors, the onboard computer system automatically controls the steering wheel, the gas pedal, and the brakes. The direction the cameras are pointing may also be controlled by computers. In 1987, VAMORS demonstrated worldwide top performance on a new stretch of Autobahn not yet turned over to the public. It cruised at various speeds with top speed of 96 kilometers per hour, limited only by engine speeds, over a distance of more than 20 kilometers. Since 1989, it has also been possible to recognize obstacles. As a consequence, it has been possible to achieve the transition into a convoy driving mode. Since the early 1990s, it has also been possible to perform lane changes autonomously. In 1993-94, in the framework of the third phase of the Eureka project Prometheus, 3 Mercedes-Benz S-Class passenger cars were equipped with University Bundeswehr vision systems based on new micro-miniaturized TV cameras. All electronic equipment now fits into the trunk space in order to achieve better maintainability and accessibility. However, in the UBM vehicle VAMP, part of it has been mounted on the right back seat. Up to 6 other vehicles may be tracked in parallel in both the front and the rear hemisphere. Their state relative to the ego vehicle is estimated concurrently at a rate of 25 Hertz. On this basis, at the final demonstration of the Prometheus project near Paris in October of 1994, on a 3-lane freeway with normal traffic, the capability of making the decision for lane change fully autonomously was shown for the first time. A module developed by our computer science partners at UBM tracks the entire traffic situation around the vehicle, especially in the neighboring lane to be changed to.
Okay, so if you actually listen carefully, you would see and hear actually the all of the keyboards and all of the technologies which are actually present even today in today's autonomous vehicles. And the last maybe 20 years of development, more or less, we try to actually achieve better performance in some sense. But a lot of things were quite already done at that time. So, and if we take into consideration that at that time the computation power was very limited, so most of these works actually were done on a custom computer. So they were developing also some custom computers to deal with computer vision and so on to work on this topic. And as you said, so it was some things were done on 20 Hertz, so 20 times in second processing so there was a lot of drawbacks as we know today, but still it's quite inspiring at that time that what things were achieved. So later there was in 2005 there was a DARPA Urban Challenge.
Welcome to the DARPA Grand Challenge. The objective,
just
create a self-navigating autonomous vehicle that can safely drive 132 miles through a harsh desert environment without human intervention. Yes, these are robot cars, and if you've ever wanted to see the future, take a good look, because it's right in front of you. The technology we see here will be used in the military within the next few years, and eventually, robots like these may be taking you to and from work. But it's not easy. 43 teams from around the country began with dreams of building a robot capable of conquering this course. Only 23 teams earned the right to run in the $2 million DARPA Grand Challenge.
But it's American concepts, fail fast, learn fast. Yeah. So we also have in virtual vehicle several vehicle demonstrators which are able to demonstrate various automated driving tasks. I will now continue into some other aspects, so which is what are actually our expectations or motivations to go for ADA. So one of the initial accept of it being cool, so and the goal to achieve and automate different stuff, there are some very specific key more or less expectations which we have. So one is the really increased safety. So in many aspects we want to minimize collisions, although humans are very good drivers in general. If we look for the miles driven and the how many accidents we make, humans are very good drivers, but still there are yearly many deaths related to driving. And the second one is increased traffic efficiency. So autonomous vehicles also provide us as a tool to optimize the traffic. We can also use less cars, or we can maybe avoid even parking, so that vehicle can drop person to some location and just drive without looking for the parking spot. And you all know how difficult it is actually to find the parking spot in urban environments. The third one is reduced emissions. So the goal is to reduce emissions from the fuels and so on. So also with increased traffic, we already reduce some emissions, but in other aspects also fully controlling vehicle enables us to really reduce emissions even further. And you will see also some of my work is also related to this topic. And also the fourth topic is very important one. So the giving mobility to handicapped people who don't have a privilege to be able to drive themselves. Autonomous vehicles enable them also to drive. And as a final one, there are business disruptions, innovations, and also it is promoting, let's say, the companies to invest into these topics. So to make this topic a bit clearer, so there's a lot of in news and everywhere, a lot of mentioning about autonomous vehicles, automated driving, and so on. There's one clear distinction between the levels of automation in this aspect. So if we have a human on one side and a machine on other side, we have some kind of transfer of responsibility from a human to machine. And then level 0 automated driving is where the driver has a full control of the vehicle and all of the aspects of driving. Then level 1 means that the human can, and this is already present in many vehicles for many years, that, for example, a human can take feet off or hands off of the driving wheel or the pedals, and this also helps human in some sense in if it's longer drive or something, just to take a break on the legs and so on. A level 2 is when there is also both of them, so also hands off and feet off, and the vehicle is able to kind of steer and propel itself. But human is always looking at the road. So human is always practically driving and always has to immediately take the control of the driving. Level 3 automated driving is, and actually so far before this last full self-driving, the Tesla was also level 2, also marketed differently, but it was mainly level 2 in the sense of the responsibility on a driving. The level 3 is much different, because you see here that the sight is not on the road anymore, so the human can also rest a bit. So the vehicle is actually driving for some time on its own, and the vehicle is responsible to notify the driver that it's not capable of driving. So the driver does not have to oversee all the actions of a car. It should be there just as a backup and to take over the control with some meaningful time, so that it gets some meaningful prior notice that it needs to take the control of the vehicle. Level 4 is actually quite much more further. So this means that the capabilities of level 3 driving, automated driving, are present on a bigger stretches. So in a sense that if in level 3 the vehicle is able to drive autonomously in a traffic jam or autonomously on a highway or something, on level 4 actually the vehicle is able to have it longer, so either some full trip or some parts of a trip. And level 5 is driver off, so even the driver does not have to be present in a vehicle, so the vehicle more or less can do automated driving independently in all driving conditions. So how do we achieve these driving capabilities? So on one side, if we have an environment where the driver and the vehicle is operating, we have a vehicle and a driver in this environment, and as a feedback from this environment, we get some sensors which scan the environment, get some data in some sense, and so on. And we have also some map, which is kind of some database which we have, and also communication with some infrastructure. Then we have a perception, which is our software, which is processing these sensor inputs and getting some meaningful information from these sensors, or extracting some meaningful data. And then we have a planning component, which is deciding what to do based on the perception. And we have a control unit, which is executing more or less these decisions made in planning part. So for sensors, we have many different sensors: cameras, radars, lidars, and so on. You mostly probably heard about all of them so far. And in perception, we have a different tasks. So one is localization, trying to localize vehicle where it is in the world. The other one is maybe detection and classification of different components, like vehicles, traffic lights, lanes, and so on. And trying to get traffic signs, objects, and so on. And usually we have some sensor fusion, which is kind of combining all of these perception data into one meaningful data representing the vehicle environment. So I will just show you quickly here the one of the multi-sensor data fusion, which is quite interesting. So the goal is to get from multiple sensors, get the data which is even better than any of the single sensors, which is probably. And this is one from BaseLab, just showing one simple example. There is a vehicle coming from behind and overtaking the vehicle, and then using the multiple cameras, different views, field of view from different sensors, we can get some meaningful data together, and also having some meaningful representation of the environment. So finally, we come to the planning part. So this is the focus actually of all of my work in this aspect. So planning part, there are different also different topics here. So one is route planning, the other one is prediction of other participants, the other one is behavior planning, and also trajectory planning. So route planning looks at the on a level of the road networks and deciding which roads to take to go from point A to point B, like our navigation systems in the car. And then prediction is analyzing the what we get from the sensor fusion. So when we get from sensor fusion the representation of the environment, we need to more or less look into the future, what is each agent wants to do and what they will do. And based on that, we have decide on our behavior, what high-level actions do we want to take with our car, and also plan some kind of nice smooth trajectory to execute it. The control part, I skipped it here. The control part is responsible for executing these decisions. So if we have a trajectory which vehicle needs to follow, the control part needs to execute it in a sense that if there is a snow, it should keep vehicle under the control and slowly execute some driving maneuver which was decided. Okay, so are there any questions in this part before we go into some theoretical foundations? People are already asleep, or anyone alive? Just write in chat yes. Two yes, yes. Okay, 3, 4, nice. 5, 6. Okay, good. Yeah, at least we have some. Okay. So now we go into theoretical foundations on the planning algorithms, or the basis for the work which is done in the second part. So the idea is here that we cover the sampling-based motion planning from a robotics perspective, also dynamic programming from optimal control perspective. So and also EASSS as a graph search algorithm. So motion planning is actually present in robotics for quite some time, and it's this very challenging problem. So the goal is actually to find the collision-free motion from a object from initial state to the desired state, achieving or in some sense optimizing some cost. In this case, for example, you can see there is this L-shaped object, and the goal is to go from one position into second one without colliding. This is also called sometimes piano moving problem. So in a sense that when you need to move piano into some room in tight corridors, you have to always plan how to go into these motions. And if you look in this example, we can have some kind of path or motion going through this hole here, and then getting out, going around, and so on, and place it in here. And actually, there are many different applications of motion planning. It's so very widely used in robotics. It can be used for, in this case, for example, for solving some puzzles, parking, robot motion planning for robotic arms, or for autonomous vehicles. So if we look at the motion planning problem, if we have some workspace, so marked like this, so this is our workspace where robot is operating, and we have some obstacles. So for example, we have some pole here or some obstacle which robot should not collide with, and we have our robot. So in this case, this is our robot represented with X and Y. So this is a 2D problem. So robot is living in 2D world now here, and it is driving or can move freely in this 2D world. Usually, if you look at this photo, the robot should have also orientation, right? So then it's already 3D. So if we have a robot which can rotate around this point, then it's already 3D. But in this case, the robot is fixed, so the robot can only slide in this space, so going left or right, top, down, but cannot rotate around this point. And then if you look at this obstacle, what we can do is when we slide the robot around the obstacle, we can have some different shape like this, you see here. And this, in this manner, we can go from obstacle into the configuration space. So what we have now here is we have a configuration space which is in collision. So if this point of robot XY is anywhere inside of this, actually robot is already in collision. And in this manner, we can nicely formulate and reduce all the complexity from a robot. So if we have a higher dimensional robot with multiple degrees of freedom or different shapes and different geometries of a robot, we can nicely formulate the problem and reduce it to the simple problem, which is same for any kind of a robot. So our goal becomes actually in some generic configuration space, which looks like this, and we have some obstacles in this configuration space, and we have some collision-free configurations, like in previous case. Our goal is to find some path from initial configuration of a robot to final configuration of a robot, which is always collision-free. So which is always lying in collision-free configuration space. And this is our general problem, very nicely formulated, and we can have many different algorithms following solve this. So we can have some sampling-based algorithms, for example, which are trying to get some parts of robot motion, some which are in collision, we discard them, some which are living, we keep them, and so on. And we can use some algorithms like this to find this collision path. We can also have some optimization-based, where we optimize the whole trajectory in a single stretch. There are many algorithms going, for example, going from backward or making different graphs on this and then finding the path on a graph and so on. So so far in the wild, there are many different algorithms for robot motion planning. But if you understand this concept, then you know more or less the problem and how all of these algorithms work. So this is for robot motion planning. Are there any questions for robot motion planning? Okay, so you will get later also the more ideas how it looks when I show you the example of automated driving, and we will use all of these concepts applied to automated driving in different aspects. So dynamic programming, actually, maybe you learned this also in algorithms course in your bachelor's and so on, as a programming paradigm. This is more or less stems from Bellman's work on optimal control. And the goal is that it enables us to determine optimal policy for the robot in this kind of sequential decision-making problem, where we have some future and we can look the optimal sequential decision making, but it is also generalized to many different problems, and we use it for different problems, like I don't know, longest increasing subsequence of sequence of numbers and so on. So many different programming problems. In the real world problems, which are usually continuous, there are different variants of dynamic programming and derivations, but in general dynamic programming, we need to discretize, and we need to have a discrete states, and they also have some kind of graph on this problem. It is very flexible approach because usually it doesn't have any most of the crucial disadvantages which optimization-based algorithms have, like it doesn't need any convexity, it can deal with nonlinear problems, the hybrid problems, and so on. So quite nice problems. You can also run simulations and for determining the edge cost and so on. So it is very flexible, and it is based on principle of optimality. And actually, this principle of optimality is present in all of these, also in optimal motion planning, in A-star search, so on. So it's very important to understand and to fully comprehend this. So principle of optimality was coined by Bellman, and it states that if node B, so in this case here, is on the optimal path from node A to node E, then the optimal path from B to E also falls along the same path. So what it says, if B, this node is on the optimal path from A to E, this also part here is optimal. And this is quite nice, because we can use it to split the problem into smaller problems. So using this divide and conquer approach, we can split the big problem and going from factorial complexity to much lower complexity, and getting the easier solutions. So this part has to be also on optimal path. And then the optimal path totally from A to E is equal to optimal path from A to B plus optimal path from B to E. And how do we prove this? It's very actually easy. So if we assume that C exists, so that this some C exists other, and that optimal path from B to E is BCE. So we say, okay, let's assume that there is a other path from B to E, which is better than this part. So this BCE should be smaller than BE. Then in this case, this also part, so AB plus BCE should be also smaller than this part here. But it's not possible because then this is optimal, and this is not possible. So it means that this is already optimal path from B to E. And by applying this approach, we can actually we can let's say the principle of optimality. So if we have optimal policy, has the advantage that when we look into the future, or the closer to the goal of this optimal policy, it doesn't matter what was the past. So from this point, we have to look for the optimal path to the goal. And if we look into some problem like this, from state CDE, so these three state, and if we have these optimal path, let's say we have them, if we have this optimal path here, we can actually choose, and based on these costs, so we look only on these costs, we decide which more or less is optimal path which we want to take. So let's go just to look this in one example. So in our goal, we want to find optimal path from A to H, and we can do it in a sense this divide and conquer approach. So we go in stages, and we go from a goal into different stages. So in this case, we look for the node E. So this is our first stage. For the goal, for the node E, optimal path to the goal H is 3, and we mark it as a 3 here. For node F, optimal path is 1, optimal length is 1, and we mark it here. And also for G, optimal path length is 2. This was very easy because this was our only solution, let's say, or the direct solution. And then if we look into the node B, so in the other stage, for this case, for the node B, we have one option. One is to go with edge cost 1 and 2, which is in total 3. The other one is 7 plus 1 is 8, and the other one is 4 plus 3, it's 7. So we know that the minimum of these is going through a G and then to H. For the node C, we look we have a 4 plus 2 is 6, 5 plus 1 is 6, and 6 plus 3 is 8. So we decide either this one or this one, and in this case we take also G. And for node D, we look into the possibilities. So we have a 4 plus 2. So this node has a 2. So 4 plus 2 is 6. Here we have a for node other possibilities, 3 plus 1 is 4. And the other possibilities, 4 plus 3 is 7. So what we do is we take this 3 plus 1, which is 4. And when we come to the last stage, actually we have three possibilities. So 3, 2, 5. So this is 3 plus 3 is 6. In this case, 2 plus 6 is 8, and the third option is 5 plus 4, which is 9. And we take the 6, and we found in a systematic manner, we went through all the possibilities which were present in this graph to find this optimal path. Of course, this is only possible. This was not marked here. This is a directed graph, so we cannot go into. There are no cycles in this graph. And optimal cost value for from going from A to H is 6. So if there is we were able in previous part section, so here to go into stages, because we had notes on all of these on all of these breaking points, let's say, in these stages when we go through the graph. What happens if it's a graph like this? We can also introduce some virtual nodes. For example, here we have a node H virtual, and we have this edge cost as 0, and then we compute it as this. Or also, if we have a different ending nodes, in this case, we just put infinite cost on others and 0 on the final one which we want to achieve. So how does it look like for some problems? And we will see later solutions for these problems. So if we have a 2D graph with, for example, some different states, which is discretized, and we have a so we have a directed graph going from left to right, and we go from some initial state into some goal state, and we go backward. We check all the possibilities in the first stage, into second stage, then in third stage, and so on, and computing optimal path for all of this until we come to the goal, and then we have already the solution for this optimal path. So dynamic programming is a very systematic approach to go and to search for the solution, but the disadvantage is that actually we don't use any information which we have a prior information about the problem. So we only care about how do we go through this graph, and that we always have a more or less clear approach for going through the graph. If we have some further information and some heuristic or deeper understanding of the problem, we can also derive some heuristic function. And this heuristic function was introduced with A* search. So it also enables us to have an optimal policy or finding path in a graph. And it is actually valued because of the completeness, optimality, and optimal efficiency. And it is proven to be optimal algorithm for the given knowledge which we have about the heuristic function. Again, we do a discretization, and it is similar to the Dijkstra algorithm. It is generalization using some heuristic function, and it is instead of looking as we saw in the previous work for the dynamic programming, going from a backward from a goal, we also have always somehow connection to the full path. So in dynamic programming, we were iteratively building from a smaller solution to the bigger solution, and going and iteratively increasing the size of a solution or the length of the path, optimal path which we have. In the case of A* search, we always have the full path, in a sense that one part is estimated. So we can estimate it based on some information which we have about the problem, and the other one is computed directly. In this case, we always have this G part, which is directly computed, and the other one which is estimated. So for the same problem, if we look in this case, A* algorithm, thus going through the same graph, we have some initial state and some final state. We start initial node, so the goal is to expand initial node. We go these different, so G, and also estimate the other part. Then we decide which one next we do based on the value of this function, so which is equal to a computed cost, so cost to come and cost to go, and we decide which next node to explore. Then we look into neighboring nodes from this node. We estimate the heuristic function for them and so on, and then we fill them into open list, and iteratively we go through all of the problems. So as we saw, dynamic programming goes sequentially through all of the states. If we have very good estimate on the heuristic function, we can go directly to the goal actually, and without exploring any other node except node on the path and these neighboring nodes, of course. So it is a quite nice approach, and to introduce and include some prior information about the problem, but this heuristic function or estimate of cost to go needs to satisfy some properties so that we have an optimal solution. More or less, it has to be admissible, so it means that it should underestimate cost to go. And the further away it is from an exact value of a cost to go, the bigger search space it is. So it's very hard actually to devise and find some heuristic function which is close to the exact value. So we are on time, and I propose that we make a break, and then after break we do the other practical part, and we will then yeah. So let's start. So now when we are finished with the boring part in theory and so on, we can go to more interesting parts of this talk. So the goal, as we said in the title and in the beginning, the goal is to achieve superhuman or develop superhuman autonomous vehicles. So what I was meaning by superhuman autonomous vehicle, in a vague sense, this should be the vehicle which has a better driving performance than a human drivers in terms of safety, efficiency, and comfort. And also it should operate independently, to mean so autonomous, operate independently in all conditions human drivers can operate. And this is a very challenging task, defined this generally, but I will tackle here some different use cases. So different specific use cases as mentioned in introduction, and for all of these use cases we will have a different levels of vehicle dynamics fidelity, some different environments, and performance measure. And as we said also in the introduction, focus is on vehicle intelligence. So we are focusing here on decision making and control problem in more general or more details, sequential decision making and planning algorithms which solve this sequential decision making problem. So what were the contributions here? So there are some theoretical results on energy efficient driving. So this is for eco driving use case. Then some formalization of a general planning problem for automated driving. So scalable to wide range of scenarios in urban traffic, especially when we have a different traffic lights, lane change, lanes, multi-lane, and so on, different traffic rules. And also I will show you some resolution complete optimal kinodynamic motion planning algorithm. So coined as BOMP. And we will solve using this algorithm some challenging autonomous vehicle use cases. So some kind of multi-lane eco driving, then multi-lane with traffic lights, minimum lap time on a road, so with slippery roads with arbitrary shape like a drifting and so on. Okay, so if we look and if we said autonomous vehicle, to achieve this superhuman autonomous vehicle, 3 use cases are presented here. If we have time, and we will maybe tackle also parking part, which was done after my PhD thesis. So the first one is energy efficient driving, and we employ planning and control methods. So the goal here is to find plan motion of a vehicle going from point A to point B using the least energy while complying to all constraints. Usually in this first eco driving problem, we will just consider speed limits and also single lane driving without other traffics. And you will see that this is also done in this community which is dealing with this eco driving problem. But we also use map data, having the information about the shape of the road. So if we have a, for example, this is very common, and there are also some assistive features in trucks, for example, if there is a road in front of us with some hills and up hills and down hills, we kind of adapt velocity to kind of keep the velocity higher before the hill, then reduce the power a bit on a hill, and then also use the gravity after the hill to speed up. And there are actually a lot of challenges here, because mainly in all of these aspects, the main challenge is computational complexity. So how do we compute the solutions in real time? And when we go through the problems, which we will see later, the real time kind of requirement varies, because for some problems real time is 50 seconds. Here, for example, real time is also 4 or 5 seconds, because we don't do it let's say repeatedly. We just do it once after some time, and we can compensate for a few seconds of computation. The challenges others are nonlinear models. So we have a quite complex models. In this case, we can have an efficiency map of an engine and so on. And also we have a very long planning horizon. So this can be a 40 or 50 seconds in future. And we have combinatorial aspects, which also prohibit the use of some methods, specific methods. And mainly works related here are based on dynamic programming and A-star search. And we will see later, actually, the main contribution was actually the efficient implementation of dynamic programming, but also this novel heuristic function, which we introduced previously. We developed the novel heuristic function, which helps to speed up A-star search and giving optimal velocity. So the model details for this problem are actually quite simple. So if you remember high school physics, we have a object on a slide, and we have some road slope with alpha. We have gravity pulling the vehicle down. We have a component of gravity pulling the vehicle down the road, and we have a motor pushing through wheels and pushing in front. And we have the simple physics. So the difference in force over the mass gives us the acceleration, or the first derivative of velocity, and the second actually the derivative of a road is velocity. So we have a double integrator here, so velocity, position, velocity, and acceleration. And we have the acceleration here, and also our control is this torque, or the force, we give and command the vehicle motor force, and we have some resistive force on a vehicle, which is mainly air drag. So this is the air resistance of the vehicle, which is kind of pushing through the air. And then we have a rolling resistance. These are all the frictions and losses in here. And we have a gravity resistance, which is, as shown here, the gravity component, which is pulling the vehicle back. And on the other hand, we have here the model of the motor. So motor has some torque of a motor, which we command. Then here we have some efficiency. So this nu is the efficiency of electric motor, which is some kind of a map. So we have the static map, which gives us what is the efficiency current of a motor. If it's electric motor, maybe 90%, 80%, depending on the region, or if it's combustion engine motor, giving 40%, 30%, or whatever. And we can scale it to the wheels, going from a motor size. And our cost function, or the goal of optimization, is to minimize total energy usage. So total energy used is the energy which we consume for the electric motor. So this is a torque of motor times omega rotational velocity, or this force of motor times velocity, longitudinal velocity of a vehicle. So this is this part. And the other part is auxiliary power. So for example, if we have a combustion air conditioning, or we have some kind of constant cost, which is proportional to time, we can include it as well. And we do this integral, and we want to minimize these costs, and also satisfying some constraints with maximum and minimum velocity. And if we split based on this formula, we can get the total consumption energy. We can split it into different components. So this was the part of my work, how I formalized, so that we can get nice heuristic function. So we split it to acceleration related work, road slope related work, roll related work, and air drag related work, and also auxiliary related work. So these are air conditioning and so on. And the road accelerated work, to get the heuristic function and the underestimating heuristic function, acceleration related work is always higher or equal to the difference in kinetic energy on a, if we consider the vehicle which is on a flat road. So always in between two different states. So in one state we have the vehicle with velocity, for example, 50 km/h. In other case, the velocity with vehicle with velocity 100 km/h. Always the used work for the acceleration is higher than or equal to the difference in kinetic and potential energy. So we only have the losses in the motor, and the losses are always negative or zero. Then if we include road slope, so we can add kinetic and potential energy, and the total difference is, if we don't have a flat road, is greater or equal to the difference in kinetic and potential energy together. And for the rolling resistance, we can actually, this doesn't depend on the road trajectory, so we can also compute it, and it doesn't depend on velocity or any other aspect. So what we see here, this one depends only on velocities of initial and the final state, and these depend only on the height, so the elevation of a road on initial and the final state, and of course also velocity, and this one doesn't depend on any of them, so it just depends on a stretch of a road. And what we are left is this air resistance and auxiliary power. So if we look into this example, as we said, the goal is to find optimal velocity based on the road slope and the vehicle model. And if we have some initial state and the final state here, so for example, here the goal is that we have some initial velocity, for example, on a distance 200 or 100 kilometers from a goal, and the final state it after 100 kilometers to stop and to have velocity 0 in this case. And we have a different possibilities, let's say the velocity profiles which we can drive. What we are left from the total energy consumption is we have initial and the final state, and these initial and the final state are so other energy components are only can be computed based on the initial and the final state without any of these trajectories. But these trajectories for air drag and auxiliary, they depend on the energy on the trajectory which we take. And we see here that we have the component of air drag and component of auxiliary. And if we look into these equations, actually we have the component of air drag. This is proportional to velocity square, and the other one, auxiliary, is inverse proportional to velocity. So this part with velocity square, we can plot it like this, and the other one, we can plot it like this. And when we sum actually these two, so the optimal velocity for the air drag is actually to have a zero velocity, right? Because it's minimum, it's zero energy lost, and also for the auxiliary power, it is actually to have infinite velocity. So when we add these two components, we actually can find that there exists. So this is a convex, and we can find some optimal cruising velocity, and we can actually find analytical solution for this. So this was a quite big achievement for us, and in general for the field. We computed analytical equation for the optimal cruising velocity for driving on a flat road with some vehicle model which we have. So this depends on an air drag model of a road and also auxiliary power. And in this auxiliary power, we can also add some operational costs like cost of renting car or paying the driver and so on. Also some economic costs can be added here. And we can actually use this to compute and to estimate with some underestimation the costs to go in this case. So what we can say for any of these trajectories, all of these trajectories, they will have greater or equal to energy consumption to just constant driving on the optimal cruising velocity in this case. And actually this can be nicely computed, this velocity, and we also later introduced with some maximum acceleration and so on, because it's not possible to just infinitely fast go from initial velocity here and also to brake, just to have it more precise. And actually this speeded up quite significantly our computations. We got the algorithm implemented directly here. So this is using some state-of-the-art heuristic function. And this is a road. We see that there is some hill. So we are driving over the hill, and we compute that our optimal cruising velocity, so our optimal cruising driving trajectory, velocity trajectory is to here, as you see here, drive constantly, and then here slow down, and then again after the hill speed up and catch the speed here. And with our proposed heuristic, actually we got a twice speed up compared to state of the art, and this was this trajectory, exactly same trajectory. And we had also some different graph search methods like forward and backward dynamic programming, but more or less the A star was quite significant. So what is the problem here is everyone, as Mike Tyson said, actually, everyone has a plan until they get punched in the mouth. So we have the energy efficient velocity trajectory, but we don't consider the vehicles, we don't consider all the possibilities, multi-lane driving, traffic lights, and so on. And then we went for extending this into general driving in urban environment, and also applicable to highway driving, but urban is more complex. So we want to achieve something like this. We have a velocity planning, longitudinal as well as in previous case, but we want to achieve that the vehicle can change lanes, go around the vehicle, get the traffic light. You see here the green traffic light and so on, and to drive generally in urban environment. So going back to the motion planning problem. So as we said in the beginning, motion planning approach with configuration space actually gives us possibility to very nicely formulate the motion planning problem. So we can go from a very complex problem, having the complex vehicle or the complex robot geometry and kinematics and so on, into the problem of finding a path in configuration free space. But the computation of the collision free configuration space is far more complex than finding this or at least the same complexity level as the motion planning problem. So for the automated driving problem, as we saw here, where we have the vehicle, ego vehicle is the yellow one which we control, and the purple one in front of us, and the traffic light in front of us. Actually, we have one dimension which is S along the road, one is lane in which we are driving. To go from this dynamic problem, we can add the time as additional axis, and then we spend this space which is static. So for the traffic lights which we have, this traffic light will represent some obstacle like this. So this traffic light is green here. We can freely drive through here, but after some time, this traffic light turns yellow, and then later it turns red. And this traffic lights actually, when it's turned red, we cannot drive, let's say, here through this region here. On other hand, the vehicle which is driving in front of us can have any arbitrary shape. We need some prediction what the vehicle will do into future, because we are adding this time axis, and we need some prediction about what the vehicle will do in future. And in this case, we can have a simple prediction that the vehicle will have a constant velocity, but this can also be something more complex. We can have some kind of funnel based, like that as uncertainty grows, that this vehicle region becomes bigger and bigger, and we have some minimum acceptable risk with the region where we don't want to go, or this is all deterministic, but it can be also extended into some probabilistic, so that we have some kind of cost going into some regions. Okay, so our goal is, as we said, is to find some collision-free path which is satisfying vehicle dynamics, which is very important in this case, and going around this vehicle, and also avoiding traffic lights. So what we developed for this aspect is this search-based optimal motion planning algorithm, SBOMP. It is based on the A-star heuristic search as before. The key difference is that we use so-called motion primitives, and motion primitives are the atomic motion parts. So we have these small atomic motion parts which are collision free, and which are also satisfying vehicle dynamics and in general which are feasible for the vehicle to execute them. And these parts let us to go from initial state. So if we have some initial state into reachable neighboring states, they are also in some sense sampling. So we sample all the possible actions vehicle can do around, and we can build a graph iteratively and using some A-star heuristic search algorithm for some horizon in future, we can plan some motion. So we use this horizon in future. So this is actually MPC approach. So maybe you heard about model predictive control. We plan from initial states for some future horizon. Let's say in our case, we have a hybrid horizon based on the distance and time, and so in this case, if either distance or time is reached and we have a collision-free trajectory which is reaching the horizon, we have the solution, and then we execute one or few samples from this plan, and then we replan again, and then we do this iteratively after in the loop, let's say, after with some frequency. So we either 50 hertz or 20 hertz, depending what we can achieve based on the computation. So the difference here from the previous A-star search is that previous A-star search was fully discretized. So we have a discretized problem, and the discretized problem, actually, we already have a graph, and then we go into this graph. In this aspect, we use the concept from hybrid A-star, which is actually practically searching in continuous space. So we don't discretize state space. Any continuous state is possible, but we sample the actions which we do. So by sampling actions, we have the neighboring states which are fully continuous, and we map them actually in which bin do they fall in. So using the hybrid A-star approach, we will see in the next step, we bin them, let's say, based on the some discrete bins. And we use some relaxation-based heuristics for guiding the search. So the idea here is that we have an efficient search because we have very efficient heuristic function. We pre-compute heuristic function for the whole trip based on the previous approach for energy efficiency, and this gives us very informative heuristics in urban driving or highway driving. And we also have the component which is anytime. So if we kind of spend the planning budget, so if we have some planning time budget for, let's say, 50 milliseconds, when we spend the full planning time, we give the solution which is the longest one. So the longest solution which we have, we give it back. And this is how the A-star works. As we introduce in theoretical part, the heuristic A-star search has a closed list and open list. And open list consists of the nodes which are reachable from the initial path and initial state. So we have some initial states, as we showed before. We expand the initial state. We look the all neighboring states, and all the collision-free neighboring states we put into the open list. And in a greedy manner, we take the next one, so the best one from open list, we expand it, and also we move it. So we select it in some manner. Usually we do it greedy. So based on the value, we take the greedy one and we expand it, and then we move it to the closed list and remove it from the open list. And then we do this iteratively until we reach horizon. So while we are within this horizon here, or either we reach the computation time budget which we have. So a very important aspect with this expansion. So this expansion means, as we said, we go from some state which we on an open list to look to neighboring state, and we sample it based on the motion primitives. We generate, we get in this aspect, we then get the children and from this node, and these are all nodes which are collision free. So for the case of automated driving in urban environment, we construct motion primitives like this. We have in this case, again, we have here actually not again. So this is the first formulation in this way. We have here on one axis which is position along the road, and another one is time. And when we plot initial velocity for a node, it represents the slope here. So geometrically, the initial velocity is a slope. So we have some vehicle which is on some position with some velocity. And this initial velocity of a vehicle constrains our initial slope here. So to be feasible for the vehicle to execute this path, all the neighboring paths have to start with the same velocity. So to have it continuous. And from this velocity, we sample different accelerations, and we can have a different from this would be the maximum acceleration, and this would be the minimum acceleration. So this would mean the maximum braking. So that vehicle fully brakes, and this is the vehicle fully accelerates. And then we have many samples here. So in this case, we show 6, but in general, it can be much more. We have 20 or even 100 samples, very fine-grained the sampling of the accelerations. And then we let these nodes expand for some time and distance horizons, or step. So we have a time and distance horizon, and also for expanding of these motion primitives, which are these atomic actions, we also have a time and distance steps. And this gives us longitudinal motion variance. So from some initial state which we have some longitudinal motion variance for these states based on just longitudinal acceleration. What we have also is we have lateral motion variance. Lateral motion variance mean that we have also some steering possibilities. And to have a very efficient algorithm, I didn't mention before, so the finer this sampling is, actually we have a bigger space. So we have a bigger graph and much more. So this is a branching factor in our graph. If you remember, or if you watched like AlphaGo or different algorithms, in AlphaGo branching factor is around 200. So if we do something like 200 samples here, we are already close to what AlphaGo is doing. So we have to nicely balance this, the branching factor, and also the quality of our solution, because if we just do 2 or 3 samples here, then we will not have a nice solution at the end, because our algorithm is resolution complete and optimal. So the lateral motion variance, we decided to have it nicely, only 3 lateral motion variants. One lateral motion variant is staying in the lane. This means that we just stay in the lane and we don't change the lane. And what is also the good thing is we actually constrained our planning to the coordinate frame which is following the road, so which gives us also kind of additional efficiency, that we don't have to plan the continuous trajectories. We just plan in the coordinate frame of the road, which is called FreeNet frame. So you can find the references in the work which I added to Drive for this. And then we have an action to stay in the lane. The other action is lane change right, and the other one is lane change left. And we define this lane change to be feasible, so that to have a possibility to, because we cannot instantly change a lane, we have some defined, this is a hyperparameter time of lane change. So we say that, and we analyze some human driving studies. This lane change time is around 8 seconds. So it's enough, around 8 seconds to change a lane for the driving. And in this case, we also reduce this kind of continuous driving in a sense here, because we would also need to consider orientation of a vehicle and so on. We can consider it to some kind of motion like this, where we have some discrete lane change possibilities and linear changing between the lanes. And then if we are in the middle of here, for example, we can use it to continue expansion of nodes and so on further and very efficient manner. And then when we combine these two variants, for example, in this case, we can have a different lane change left variants, and these are stained lane variants. And also, I didn't show, but it's just symmetrical here, lane change right variants. And then from some initial state, we have all of these different variants based on the initial velocity and the position of a vehicle. And if, for example, vehicle is in here, then we will have lane change left variants starting from this initial state. So by using these motion primitives in this search-based optimal motion planning framework, we can actually construct collision-free and collision-free and feasible driving behaviors for our vehicle. So we developed this algorithm, and it is working. And then we wanted to validate it. I will not go actually too much into the validation problem, but just to mention is actually the different possibilities to validate. Actually, I will have to go a bit more into details on this. So this is automated driving problem, as we said, not eco driving, but automated driving problem, where we can have driving on multiple lanes with traffic lights and so on. And the problem is how to actually validate this and to show that we have a superhuman automated driving performance. So we need to have it driving, let's say, in a real. and actually, we did some kind of also in this aspect some divide and conquer approach. So we split the problem into decoupling the problem into different smaller problems and then validating them individually. And you will see how we did it and how this actually enables us also kind of economically and practically to be able to do this. So if we have a different aspects of a driving, we have a human driver, we have an AI driver, we have a passengers, the vehicle dynamics, infrastructure, other traffic participants, and also reproducibility. Because of each validation, we need to have it reproducible, that we can also test the results. And these are different validation approaches. So we can evaluate it on a public roads, but this also, for example, doesn't give us reproducibility, because we cannot reproduce some arbitrary driving situation which we have on a public road, because every driving situation is unique in some sense. Then we have the vehicle and traffic simulators, which are quite good, but they are not real. And also we can have a driving simulator, as we will see, and also we can have a driving on a proving ground. So what we did here is we tested this search-based optimal motion planning framework for the automated driving in this manner. So we took the realistic traffic situation. We modeled this traffic situation with the road structure, the traffic lights, the other vehicles, and the kind of the frequency of a road and so on. and especially the timings of traffic lights, so how they change from green to yellow and to red and so on. Then in parallel, as we saw before, we developed this automated driving software and in simulator, and also we took the driving simulator study. So we took the how usually humans drive in this same traffic situation, and then we combined these two results, and then we tried them on a proving ground to compare actually how automated driving is compared to the other actually human drivers. So during my secondment in Sarajevo at Electrotechnical Faculty, University of Sarajevo, we took this stretch. Actually, this is the main street, main urban street with 3 lanes and 3 traffic lights, which we considered. And we modeled this in a sense that we made it in the simulator and also some high fidelity simulators. And we see here our eco vehicle. So the white vehicle is the vehicle which we control. So this is the custom made traffic simulator. And the white one is our eco vehicle, and in different colors are other vehicles. This is a 3-lane way, and we have a traffic light here. And as in previous case, as we showed, so if we look the projection, so imagine this as this 3D problem. So we, as in this case, so we have the S is distance along the road, L is lateral, so lane, and the time is third axis, which makes this problem static. And this traffic light becomes this obstacle here. In this case, it's here. So this traffic light becomes this obstacle here. And all of these vehicles are predicted that they will keep a constant velocity like this. And then we look into the future, and then we need to find the optimal velocity for the vehicle, which vehicle should drive, avoiding the collision with other vehicles, but also which is smooth in a sense that it is dynamically feasible for the vehicle to drive on. So for our ego vehicle, you see here that we already have some plan here. The plan is to drive in the middle lane here, and then here start changing lane to move to the lane left, and then continue in the left lane. And in the velocity, or this ST projection, we see that the vehicle has some velocity here. So the vehicle drives on a higher velocity. And you see here this red vehicle in front of us. Actually, this represents this region here. And as you see here, actually, this red vehicle in front of us is the last one catching the green light. So if we just follow this vehicle, we will actually come here to yellow, and then we will have to stop. So because vehicle is programmed not to go through yellow light. So the vehicle actually decides that it needs to overtake this red vehicle in front of us. And this achieves by catching up behind this vehicle. So it comes to this gap here. You see here also this green vehicle is here. So the vehicle here is in this gap in between these vehicles. And then as you see here, the gap is here, and it's already approaching the gap. So it means that the left lane is free, because it will be in the gap between these two vehicles, and then it can go actually and to change lane, and then it slowly changes lane until when it changes lane here, the vehicle passes the red vehicle here and passes through the green light. And now you can see it actually in animation. So you see here that in MPC fashion, we plan every time step, and then we plan for some horizon in future. You see that we actually, the traffic light turned and all the vehicle behind us stayed, and we took this vehicle. You see that this also vehicle will actually have to stop here because it cannot go through yellow, and we are able to go around this vehicle. And how does this work in background? We using the motion primitives, so motion primitives, and we sample this search space. And you see here that we are now, actually, I will go again. You see here that we try to drive constant velocity, but we are colliding with this one. Then we are looking for some possibilities to change lane. Here we cannot directly change lane because there's not too much room, or we need some time to change lane. So we go back and try to change lane before, and so on, until we find this nice collision-free trajectory. And when we find the collision-free trajectory for the full horizon, we execute it. And then we plan again in background until we find the next horizon. So we tried this also in some high fidelity simulators. So this is considering the more detailed vehicle dynamics. And also we tried this in driving simulator studies. So this is the same, exactly the same road, just different environment, but it's not so important. And we took the study, and we took the around 30 participants which drive in the same environment. If you don't know much about the driving simulator, this is the cockpit, very realistic, and it looks like the same as the car, and the driver can drive it, have a steering wheel, and so on. And then around him, it's like 180 degrees full immersion screen with all the mirrors and everything. It's getting the feedback from simulation and allowing the driver, let's say, to drive in a very realistic environment. To have a input from all the drivers in the same driving situations, we made it such that when driver drives here with constant velocity around 50 km/h, the scenario is triggered, and then it can drive however he wishes. And all of the drivers, they did around 6 runs, and you see here that the traffic light turns yellow and red, and this driver went through the yellow light in this aspect. And then we did this for the 30 drivers, and around in total, I think 100 or something trajectories, and all of these trajectories are shown here. So you can see here that this is the full stretch, around 1 kilometer, and we went. You see that the just a second. Sorry, just a second. So do we have a question? We have a question: is Cockpit open source and free? So in our case, we use this commercial. This is commercial driving simulator, but I think there are also some open source. I'm not sure. There are some open source also simulators, and we had also one previously which was open source, and you can build it with screens and also gaming consoles and so on. So we had also something like this. So for the driving trajectories, we plotted them here. You see that actually different drivers have a very different trajectories with changing lanes and so on. And also when we look on this ST projection, we have the traffic lights here. These are our 3 traffic lights, and we see that some of the drivers stopped on the first traffic light and then continued. One driver even stopped on the second traffic light, so he or she didn't catch the second traffic light. Then some here stopped on the second traffic light. So this means here that this is actually third traffic light, but the second time instance. So this traffic light is first time red, then the second time it also turns red. But also some drivers went through straight here. And also some actually, when we look to the velocity, so these same trajectories and some filtered, they are actually have a, you see here that many of them actually were driving above the speed limit, so they were breaching the speed limits, even some going around 75 or something here, as you see here. And these are the trajectories which are stopping on the first traffic light, on the second traffic light, and on the third traffic light. And you see that we can nicely visualize all of these, because this was the study which was running for several days and many drivers and many runs, but we can also very nicely visualize them on the same graph here, and also cluster them in some different and analyze them properly. So what we found out that actually the let's say actually for all of the drivers, we also told them that they can also drive normally, and also how they usually drive, and also we gave them some inputs to drive energy efficiently also. But what you can see also here, that we had also some collisions. So we had 2 collisions occurring in this aspect in 100 trajectories, and 50% of the people actually broke the speed limit, and 12% broke with even plus 10 kilometer per hour, and 70% went through yellow light. So this is actually, we intentionally made this very tricky. So even the scenario which was taken, it was not so trivial. So it's actually, people had to be, take care that they not break or that they actually don't stop, that they don't go through yellow light, sorry. And what is also interesting is that actually our optimal, so when we compare to automated driving, actually is 60% better. So our optimal one is 60% better, or 60% better than this one. So this is also how it looks, the same driving, but we saw actually I don't think it's same. This is also from simulator, and we can see that how the one of the optimal driving trajectories. So actually not optimal, but this is a human driven, but close to optimal. So this is one of the best of human driven, and you see here that it takes the first traffic light overtake, second traffic light, and so on. But what this driver foreseed is that actually it went here into this kind of trap, and then it could not avoid going around this vehicle. And what happened is actually, I think this was the collision one. Yeah, you see, close to collision. So the vehicle in front stopped, and then this one had to really hardly brake. So it was very challenging, the very challenging scenario, and it was a lot of very nice feedback from the driver. So they felt very challenged, and even they did like the same scenario for 6 times. They would not get bored, and they would find different ways to go around and so on, and some even made the collision. So it was very nice actually study. So what we did then is we took these trajectories which were done in Graz, so in virtual vehicle, and we got these trajectories from a driving simulator and automated driving, and we tried them on a real vehicle. So we got this very fancy S90 Volvo with steering robot, so to articulate the steering wheel and pedals, and we tested this on this full stretch, which was also around 1 kilometer. And here we just took the 3 lanes and also virtual traffic lights. So how does it look? So you can see here that this is a human driver, one of the examples, human driver passing through yellow light. You see here that these are vehicles from simulation just embedded into post-processing of video, and here this is the trajectory. You see that this driver passed through yellow light. Then in some other case, this is a human driver which is actually heavy braking, and we achieved 15 meters per second square, which was more or less the limit which was in data sheet of a vehicle. So it was quite challenging. And the last one, as you saw, is automated driving, which is planning in advance and going through the yellow light, as you can see here. So you see here that it's actually already overtook this vehicle and then passed through the green light. And what we did afterwards, we took some human participants and we took them into the car, and then we asked them to fill in how they felt being driven by the car. They didn't know which trajectory was by human driver or which one was by automated driving. So they just feel how they felt, and actually we got that automated driving is better, and they rated automated driving the best from these. And you can see this is the optimal path. So the vehicle overtakes and goes from second lane or middle lane to right lane, and then goes back and passes. And this is the velocity profile. Yeah, so this is the kind of conclusion for this automated driving part. We decoupled the problem. We got a very nice motion planning the algorithm, and then tested them nicely and achieved superhuman driving performance in comparison. So do you want break now, or we can continue directly with the other use cases? If no one is complaining, I would suggest at least 5 minutes break, just so that I can get my voice back better. Okay, great. Quick break, sounds good. Great. Do we have any questions so far? So maybe can someone turn on the microphone and ask something, or so this would be good feedback for me. I'm sure you have some questions. Or it was
hi.
Okay, yes.
Hi, Zlatan. Yeah, I was just wondering, a lot of the kind of test examples that has been run through here are like, American style highways, motorways, things like that. Is there much testing going on with more like city driving, kind of like European, like smaller streets, things like that? Is that harder to deal with? Is that a different problem?
So this is actually quite good, very good actually question. So this is also a bit, I would say, a little bit old work now. So this was from 2018 and so on, and also which was already quite challenging. And we will see later in the end. Actually, I will give you that these things which you ask, like a small streets and these cuttings and so on, actually this is also already it is not fully solved problem yet. So there are some solutions and some kind of hacks how to deal with this and so on, but it's not solved in a kind of complete way and giving the complete algorithm and optimal solution and so on. So this is still not solved, because we will see later that it's very challenging problem. So this becomes kind of interactive driving and fully multi-agent problem. So far, actually, I didn't mention this, like In my case, it is kind of multi-agent scenario, and I'm dealing with multi-agent problem and so on. But eventually, the planning is single agent. So I have a prediction, which is for other traffic participants. So I predict what they will do, and then I plan for this. And there is no any kind of game theoretical aspects in this case. There are people also for some time trying to get some game theoretic aspects, and they are quite nice, but all of them have some kind of limitations, and they ignore some other parts which we deal here. This is the combinatorial optimization problem, and we deal with the combinatorial aspect. So we have a combinatorial aspects in the sense that either we brake on a traffic light or we speed up and go through green light. So this is kind of very distinctive different maneuvers, right? So it is not yeah, you cannot convexify this. And there are some ways to, if you have a convex solution, that you kind of can have also game theoretic aspects in some kind of iterative convex solution and so on. And this is also very complex in a sense that you have many traffic participants at the same time, many traffic lights or different roads signs and so on. So many different constraints to satisfy. And if you have a convex algorithm or algorithm which exploits convex problems, then you have the problems. But we will see also and discuss this into more details later.
Cool. Thanks very much, Zlatan. Thank you.
Yeah. Okay, so are there any more questions, or we go directly for a break? Okay, no one is complaining, so we go then for break. I would suggest maybe I would say again 10 minutes just to get back. We have actually also very interesting parts later. We go also into drifting case and also this interactive driving and also parking. So I hope it will be, if you were interested with this previous one, I expect you will be interested in this. So let's continue. So the next part is performance autonomous driving. The goal here is actually to drive on an arbitrary shaped road. So arbitrary shaped road with very slippery, and as you see here, the blue vehicle is drifting around and losing the control in some sense and going around these curves. So for this, we need different vehicle models. So this is much different. We saw first, for the first step, we needed only longitudinal vehicle model with some physics and engine control and engine modeling and so on, but still some two-dimensional problem. Here we need, in automated driving, we needed, let's say, four-dimensional. So we needed longitudinal velocity, we needed distance along the road, we needed lane and the time, and maybe direction of a lane change, and that's it. And in this case, we actually need much more complex model. So we need to model the track, the track and the wheels forces. We have a fully vehicle which can fully slide on a route. So we already have here 4 or 3 dimensions just for the sliding and so on, without velocities and so on. So it is quite challenging problem. So what we do is we do some vehicle model approximations. One is semi-linearized single track model. This is a quite usual model, and we will see also later for the parking we actually use similar model as this one, and we use it on a not so aggressive driving. And other one is model we use is so-called, because drifting is very complex, a lot of different force interactions and so on a wheel are very tricky, and it is the full research on its own. Like a lot of people spend their careers like Pajeka and to modeling and so on, just the wheel forces. So what we used here is actually quite interesting approach using equilibrium states. And this was actually known, and also for people who do drifting and so on, you know that you can actually drift around in some circle around and with some constant velocity, longitudinal, and also constant radius. And actually these equilibrium states, what are they described with? They are described with longitudinal velocity, with beta steady state. This beta means this side slip angle. This would, in this case, show the axis of the vehicle and the angle between axis of the vehicle and the velocity of the vehicle actually. In normal driving, when we drive without drifting, usually the beta is very close to zero. So our velocity is always in the direction of the vehicle, right? Only slightly when we change lane and steer, but not so much. But when we lose control and when we do drifting, this beta can be quite high. And this psi dot represents psi represents orientation. So like in the plane, the orientation of the vehicle, and psi dot represents the rate of the change of this. And this actually is with the combination of this psi dot and velocity, we get the radius of the curvature. So we can also get this radius of this circle here. And actually, the full vehicle model is quite complex. So we have a very complex model, but for the equilibrium states, we use these 3 states. And for this semi-linear track model, we can also use very simple model without much of the, because for this is for low side slip angle. So this one we assume as more or less 0. So how we do this with equilibrium state manifold? So what we did is we numerically, before anything, so in advance, we compute all of these equilibrium states. So if you look at this here example, we can actually have many different examples here. We can have a with same radius, we can have a different velocities, we can have a bigger radius, smaller radius, and so on. And we impose these constraints to have it as such, to be them as 0, so to be equilibrium state. And then we have 3 equations, 5 unknowns, and we fix this radius and beta, and then we find these 4 other components. And so we define this for the radius of curvatures between 10 and 50. We just sample them and do it for counterclockwise turn. So for example, here you can see that this is a 3D space where we have a beta, psi dot, and velocity. So these are these steady states. And we show, for example, here for some radius starting, let's say around 10 meters radius, we have some dots here, and these dots actually are representing different beta and psi dots. So actually psi dot is kind of constant because it's 10 meters, and it also depends on velocity. So we have a different set of states here. And for example, some state here would represent some driving like this. So you see here that it's a very low velocity and we have some very high beta. So we see that the vehicle, because usually velocity is in this direction and vehicle axis is like this. And then we generate for different radiuses. So for example, some different radius here, it would be something like this. You see that velocity is also higher because there's a bigger distance between the vehicles, and so on. And here, for example, velocity is even bigger, and radius is also bigger. And then we interpolate this with some curve and use it as such. And if we look into the right and left, we have some on this animation, you can see that we have some state manifold or the sample dot like this. And then when we interpolate them, we have some manifold looking like this. And if you look from top, you see that there is a one side here and one side here, and this is more or less driving straight road. So this is not very well connected here. So what we do here is we also, with semi-linearized single track model, we get this region here. So we have the yellow one is covered by both models, and the black red one is covered only by the bicycle model or semi-linearized single track model. And in this case, we can have a quite nice motion. So we can nicely plan motion going from for example, drifting on one side, going to a straight bit, and then going to the drifting on the other side very continuously and without any hassle. And actually, this was a quite big advantage compared to other approaches presented, because in other approaches in literature, state of the art, they would manually cut and they say, okay, you drive into the curve here, you go do this maneuver, then you exit here, and so on. In our approach, it's very general, and for arbitrary shape, the algorithm in the MPC approaches, so planning for the horizon in future, plans the best approach for each of the maneuvers. And it can also exploit also straight driving and drifting and so on. So it's very general approach. And this actually is very much because of this here in bridging between these two, and also using many different states. So in other approaches, they would have manually some of these states and not the the full equilibrium state manifold. So what we do is same as before. We are iteratively building graphs, and our graphs graph consists of the node, and node is actually now quite you see here 6-dimensional. So as we saw, for example, in the case of eco driving, the state is only distance and velocity. In this case, it is 6-dimensional already, and we have a fixed time step for motion primitives in this case. And we use these two model for the modeling motion primitives. So we have a semi-linearized single track model expansion. This is only for low curvature driving, so close to straight driving. And we do different variations on inputs. So delta is a steering wheel and lambda is a wheel slip. So this is a longitudinal acceleration. Yeah, equivalent. And we use these two variations to generate different motion primitives for low curvature driving. So this is a semi-linearized single track model. In this case, you see that these are 6 different motion primitives, but in practice, we have like 20 or 30 of them. And you see here that we have 2 variants for longitudinal acceleration from initial velocity. These are more or less the same longitudinal acceleration, and these are 2 variants, and we have 3 lateral variants in this case. But in general, we have like around 600 different motion primitives, and you will see in simulation later how it looks like. And for the equilibrium state manifold, we also do expansion whenever possible. So for both of the cases, we do whenever is possible based on the map which we saw before. So the previous map actually tells which one is possible to do it. And in this case, we do just equilibrium states, and we deviate a bit from the surface, and you will see later. So you see here that this is some initial state. We already have some beta, as we said before. So this is a longitudinal velocity of the vehicle, and you see that it's not fully aligned with vehicle orientation. And we effectively also sample here only 2 dimensions. So we said here the state is 6-dimensional. So it's very hard to sample efficiently and nicely cover to have a nice solutions in 6 dimensions. But using equilibrium state manifold, we effectively only sample in 2 dimensions. So in beta and psi dot, and for each of these we have appropriate velocity which lies on the equilibrium state manifold. So this dot here, for example, maybe represents this initial state here. Then what we do is we project this state on the equilibrium state manifold, and this should be very close to the surface. So it's ideal, never also because of the numerical computations and so on, it's never almost never exactly on the surface. But we have some trigger, like when it's close to the surface, we can project it. Then we do the sampling around this state. So we sample some states around, as we said, based on the beta and psi dot. And then for all of these states around on equilibrium state manifold, we discard the states which are which have the more or less too big difference on velocity. So velocity difference, and then we using this simple kinematic model. So this is purely kinematics. We expand these states based on this new state, linearly interpolating this current and the future state. And we get some motion primitives like this. So you see here that these are different left curving and drifting states, and they have a 4 motion variants here, but in practice we have much more. And in the motion planning framework, it looks like this. So again, we are building trajectory by concatenating motion primitives. So as we said, motion primitives are dynamically feasible, and we concatenate them, and satisfying these concatenation rules, or taking the initial state from previous node or ending state from previous node as initial state from a further node, we have a full continuity of these states, and the possibility to kind of feasible for the car to execute it. And actually we do, as we said here, task and motion planning problems. So we actually by doing this kind of 2 models, we effectively tell, and this is combinatorial optimization on its own, to tell the car when to go into which mode. So we have like a straight like driving, then we go drifting, and then go back again straight driving. So in a sense that this is a task and motion planning problem, same as before, where we have a lane change left, lane change right, keeping lane, and so on. And we do hybrid expansion, as we showed in previous aspect, with closed loop steady state drifting with equilibrium state manifold and semi-linear single track model. And same as in automated driving case, we have this A-star based framework. We initialize with some initial state. So we have some initial state here, which is looking here. So it's more or less driving straight, beta is 0, and psi dot is 0. So it's more or less driving straight. From this state, we look at the neighboring state. In this case, we only expand using the semi-linear single track model. We remove the states which are taking the car off a road, and from the states which are there, we expand further. So taking this one here, we expand it further. They are all collision there. Then we go from here a little bit to the drifting and so on, and then we expand in this manner with A star until we find the solution which keeps on the horizon. In this case also you can see that this trajectory is kind of taking the car, because the horizon is short, off a road, but still, because we are doing in the more or less moving horizon fashion, when we are here, we will again replan. So this car will be able to stay on the road. And this is how it looks in the simulation. For the car, you see that we plan for some horizon in the future. We go around the corner, and then we drift right, then we go and drift left, and so on. So it is quite general and very good solution. And in the background, as I told you, we have around each step around 100 different motion primitives. We remove which are collision leading to collision, and then keep only the collision free left. And you see here that we plan until we find some solution which keeps the car on the horizon. You see that it's very challenging because it's going into other direction later, and it has to find some which is further away. So some solutions take quite some time, and on a straight actually it's much shorter. Okay, so this was the problem of drifting. Are there any questions for this one? So we didn't have actually chance to test this on a real car and so on, but in simulation it showed quite well. The solution is quite fast in a sense that it is not real time and in a sense of 50 milliseconds or something, but we get in 1 or 2 seconds, I'm not sure, we get the solution. And also this represents the bit of higher level planning. So it's not directly for control. We can also have a faster inner loop, which is doing the execution and the planning, or the like MPC, which is executing this one. So this gives us more on the side of what to do and strategically how to approach this problem. Okay, any questions? Or then we continue to the autonomous parking problem. So this was the master thesis from Bhargava Dabala, the colleague who worked on the master thesis project with us. And the goal here is to find the path. It's yeah, quite interesting problem, but maybe you also saw a lot of these. And it's not so easy because they are the tight environments. We need to find the large state space and so on, and we need to find also in real-time driving. So the approach here is I will again based on the search, and it's based on the multi-heuristic A-star search, which is a bit of different variant of A-star search. The one which I showed you before was single heuristic, so we can use single heuristic function. Usually, if we have multiple heuristic function, we can always take them as and to improve the single heuristic function with multiple heuristic function by taking max of different heuristic functions. So if we have a more than one underestimating heuristic function, we can always take the maximum of all of them, and this would still be underestimating heuristic function, and it would be more precise than all of them. But as it's shown in multi-heuristic A-star search, actually it's also good to keep distinctive and to include into algorithm directly dealing with multiple heuristic function, either in some round robin fashion or somehow differently. So again, we have the cost to come and cost to go, and what also Barkov tried is also using here the bidirectional. So one part is going from a goal, and so either forward, going from a goal to so going from a start to some part and then to goal estimating, or either from both sides. As a heuristic function, as we said in previous cases, these are quite important to have a very efficient algorithm, so that we solve algorithm in a best way. In A star we set G, which is cost to come, and then cost to go, which the cost to go we estimate using heuristic function, and we have the fully path cost is a full path cost, and a heuristic function makes this estimation. We use the two different heuristic functions, which are always underestimating because they are based on relaxation. So one is holonomic with obstacles. This means that we neglect the vehicle holonomic aspects, and we let the vehicle directly instantly change the orientation, as in here. We know that we neglect here these holonomic aspects, but we go around obstacles, and this one includes obstacles, and it is always underestimating, because the cost for the real car would be always higher than this one. And you see here also getting into this this part here is quite tricky. We know that we have to go multiple forward, backward trials until we get the car into this place here. And the other one is, and this one actually can be pre-computed in some aspects if we have the map or we know the vehicle in advance. And the other one is non-holonomic without obstacles. So we have also some analytical solutions for this one. So we neglect other vehicles, but we kind of take care of the vehicle holonomic aspects, non-holonomic driving capabilities and constraints. And using these different parking lots are created as obstacle map, and for motion primitives we use this simple vehicle model. We generate different motion primitives for longitudinal, forward and backward, and having multiple steering commands, similar to the one with drifting, so only for the single, so for the close to the straight driving. And we use this model, and for the collision checking, we approximate the vehicle with 3 circles, because it's easier to check is any of these circles in collision with obstacles than to check complex vehicle shape. And this is also a bit conservative in a sense. And except these small parts here, but usually it's also covered, yeah. And there is a bigger part here. So we do this collision check, and then in bidirectional heuristic search fashion, we search for the different solutions. So in this case, we use Dijkstra, which is non-holonomic without obstacles, to generate the cost to go, and then using this heuristic search, we plan the driving trajectory. And yeah, by performance, it showed to be better than other. Okay, so are there any questions so far? So these are different use cases and different use cases for autonomous driving, let's say. And we saw that all of them, they have the different kind of specialties. We need the different models for the vehicle, showing different environments, and also customizing algorithms for all of them to have a real-time performance. So questions, at least one question so far. Come on, people. There's something in the chat. No, this is from before. No questions? Okay, so we then continue for the outlook, more or less. So this is dealing with the problem of interactive driving. As there was a question before, not all of the driving are this simple, let's say. So if we have our vehicle, let's say driving here in the rightmost lane, and there is other vehicles are like this. So this is just some two example here. So we have a two vehicle here, and for example, maybe we want to go and overtake the vehicle, go into middle lane and avoid them. And what we do here is, if we do the prediction and we predict what other car will do, we predict, okay, this car will also do this. So we have a two option. We can either speed up and go before him or slow down and go after him, right? And we do with our planning, we cannot do this here. But what happens, for example, if this car as well also has the same algorithm as this one, and then they will also brake and wait for us, and it will more or less, we will have a freezing robot problem. So we will yeah, so either both of them, they stay behind and they would never change the lane, because we neglected this interactive driving aspect or game theoretic aspects like this. And then we have a freezing robot problem. We have a usually conservative behavior because we want to avoid kind of responsibility or something. So we will always have a conservative behavior. And as we know that these two behaviors, they depend on each other. So the actions of one depend on the actions on other. So we need some multi-agent based planning approach. But what is trick here? So we need to have, as we see here, we had prediction for the horizon, and then we have a planning for our single agent based planning approach. And these are all the examples shown before are like this. What we need is planning and prediction combined together. So we need to have a prediction in each of the steps. So you see, as in this case, for each of the steps, we need also prediction of other vehicle actions. And this is the game theoretic. And in this case, for example, we would see that, okay, he will brake and I will go through it. So if I do a little bit faster than him, he will brake. In previous approach is if we either brake or we have to speed up so that he doesn't catch us. So we will not consider that he will brake if we are just in front of it. So in this single agent based approach, we will for us it will be still collision if we are in front of this car and he kicks us from behind, because we have this prediction that he will have some kind of driving behavior. And we know that if we even try catch this gap before him, he will brake and he will not hit us from behind. And the problem is that when we consider all of this, actually we have the interactive driving and we can also have assertive behavior, but we have usually very like explosion in complexity of the problem. And this aspect is not so solved. I told you there are some solutions which deal with the if the problem, for example, can be represented as a convex problem or convexified, and then iteratively solving convex problem or something. But many aspects, especially in driving, in sense of the intersections or considering traffic lights and so on, they are combinatorial by nature, and we need some kind of algorithms which is very much similar actually to AlphaGo approaches. So we need to because we need game theoretic approaches, and we need some kind of game theoretic aspects in the algorithm itself. And the problem is that it is actually very complex, and we cannot find even approximated solutions, exact solutions and complete. So we need to do further approximations with neural networks or something like this, as it's done in AlphaGo, also for the simulating other agents and also for the actions. And this is a very challenging actually task, so and very common actually. So if we have some kind of in these aspects, like some rural road which is kind of not so wide enough that both of the cars can pass, this is the problem. Or if you consider even a highway driving where there are many vehicles, or it's a bit bigger jam and there is no room to go through the vehicle, there is not enough gap, so we need to kind of have assertive driving to get and to catch our gap. So actually, these are some references based on the work, and I am more or less finished with presentation. So I'm free for some questions. I wanted also to show you actually some code for this, but I noticed I'm not on my laptop, and I don't have MATLAB here and running, so I'm not able actually to show you, but I will share later with you, and you can also run maybe on MATLAB some of these. So all of these simulations, animations are generated by in the MATLAB, and you can also try for the drifting case some examples. So let's catch up the questions, and if not, yes, we have some. Okay. No one, everything clear? Am I that good? Am I that good lecturer, or?
I think it was pretty clear, but come on, guys, some questions? So I'll pose one. So you have shown some part of your presentation regarding simulators, and so you stick with on simulating cars on driving scenes. Do you take into account other aspects, other actors such as pedestrians or bicycles or things like that?
So for this, so far we didn't consider in my work. There are some colleagues actually which deal actively, and we have some also the colleague of mine on the same project, on this ITEAM project. He was also modeling pedestrians, and he focused quite a lot on modeling pedestrians and their actions and so on. So it can be also quite nicely included into this, because you saw that we also have the space, and the collisions are quite nicely geometrically represented. So you can have also pedestrians there with different shapes or any kind of obstacles like this.
Yeah. I was asking that specifically because in my group we were involved in an European project that just ended last month, And our participation was mostly focused on modeling pedestrian behavior based on what they call the naturalistic recording of how people actually behave. So the project involved having people with smart glasses in order for us to gather data and then apply data fusion techniques in order to then model pedestrians in the simulator in a more realistic way, let's say. So it kind of interacts with your talk in the sense that it would allow simulators to be more realistic and to test well, situations or unexpected situations in which you would like a superhuman autonomous vehicle to cope with. Right?
Yeah, this is quite interesting. Also, it's very hard actually also to predict what pedestrians will do, and also using some kind of different fidelity models with different using some reachability analysis, or also it usually has a lot of to do also with probability, and because it's in very few steps. If you look into the future, pedestrian can be anywhere, especially if it's small child. And if you look like 5 seconds or 3 seconds in the future, it can be anywhere somehow. And it's also quite much used with some probabilistic models like POMDPs or partially observable Markov decision processes, and these aspects, and kind of recognizing the intentions of the pedestrians and where they will do. Yeah,
right. It raises the critical issues of the blind spots that well, autonomous driving is still facing in order to be for it to be more adopted in a widespread way. I guess one of the questions during the tutorial was related with the kinds of scenarios in which autonomous driving is being mostly tested. But besides having it tested in highways with very low traffic, now they're being applied in more realistic situations within cities and so on. So there's a question by Apor.
In your simulation, do you assume that every car vehicle is following the traffic rules perfectly? Yeah, so this is a very actually good question. So in my simulation, I did this. There is also some related work from, for example, Technical University of Munich. So from Professor Matthias Althoff, and they have also quite nice. They focus on this kind of prediction of other drivers and what they can do, and using some reachability analysis, and they consider, for example, that the other drivers will follow the traffic rules, and then they have some kind of planning for the backup trajectory, so that they can always have a backup even if the other driver does in the worst case or something like this. And also if they see that the other driver is breaking the rules, then they switch to different models and so on. So yeah, this is a quite good example. And also for the previous one, for the pedestrians, there is also on TU Delft some work related to communication to pedestrians, like to kind of how to signalize the pedestrians the intentions of the autonomous car, or telling to avoid this kind of freezing robot problem. So like if for example autonomous car is waiting for the pedestrian to pass, and pedestrian is waiting autonomous car that they pass, and so on, so there should be some kind of signalization to either pedestrians, like, okay, you can go and pass the street and so on, and not wait for me, and so on. So I mean, there's a lot of work actually to fully autonomous cars, and it is also very interesting how industrial solutions are good in some aspects, using some different, I would call them hacks. So like kind of solving for all of different cases, and then restricting to these are operational cases and so on. And these solutions also bring quite far forward. but the general solution is very complex, and we saw that it's also as complex, maybe even harder than AlphaGo and these aspects to have a properly planning. Yeah. So.
Right. Any other questions?
Mm-hmm.
Okay.
Are we also considering animals crossing the road as their sense of movement? Yeah. Yeah, so these are these kind of worst case scenarios. So usually what you can also have is that in the worst case scenario, you can always check where are your blind spots, and if your blind spot is somewhere, so if it's not covered by your kind of any of your sensors, then in the worst case you can expect that there is an obstacle going from this blind spot with the big velocity. So yeah, it is quite challenging, and we can consider it with this blind spot. So what you can do is also, when it's not clear, and if you have a blind spot, then the vehicle and the planning should tell the car to slow down. So this would be natural outcome of this situation. If you have a blind spot which is very close to you, then you need to slow down, so that you can have more time to react if something pops up. So this is same as is in highway, like also the highways are constructed in that way, so that you have a highway where you have a very wide field of view, and also you have a very almost no blind spots, let's say, and this allows you to drive on a high velocities, and you always can just drive slower, and you can control this. Yeah, so actually the appropriate velocity is always the key for everything. Yeah.
No other comments?
We have some nice discussion here.
Okay.
Do you think that's it more automatic? Okay, this is quite nice. So the automated drive, actually there is some really interesting work, like how you can utilize autonomous cars to change human driving behavior, which is really interesting. Like by having a few automated cars which are in communication and doing, like from a traffic perspective, from a high level traffic perspective, if you have a few automated cars and they are driving, you can influence also the traffic itself, and you can also solve some of the congestion problems in a traffic by just controlling nicely these cars. You can kind of also amortize the propagation of these jam waves and so on, which are forming. So it is quite interesting. And for the automated cars, I probably think it will be so, and slowly they are doing this. So in a sense that this is kind of joint effort. So in this way, like we see that the problem of having a very general driving and as humans are doing is very complex. So we see that we are in each millisecond solving very complex computation problems. So we as a human drivers, we do it quite nicely with few lessons of learning and so on. We do some very complex problem, and the computer, we need algorithms and computers quite hard to solve this. And what we have so far is usually from industry, the approach is, okay, we develop the best what we can, and then we restrict so that we don't have the liability if something happens outside. So the same approach is what Tesla did. They let the people and they told them, okay, it's your responsibility. We just support you, so you need to take care. Of course, people exploit it and make some accidents, but yeah, it happens always, and also it solves some problems, and probably in some aspects there will be some kind of solutions, especially this in this interactive driving scenario. So perhaps there could be some kind of communication with signalizing other traffic, like who will take the right of way and so on. Either human or automated car tells human, okay, you pass, now I pass, and so on. So I think these things could be some kind of rule based, and some rules would solve this complexity. Okay, you're welcome.
So there was another comment on the realisticness of the simulations on excessive rain. You want to comment on that?
Mm-hmm. So this was not directly my problem, because this is the problem of perception. So usually we have a very nice very nice kind of interface. I get the information from perception, and then I do with the perception as I have, and with some uncertain. It can be also with some uncertainties which we have in perception system. So this part with the rain and other stuff, this is usually problem of perception and how it's dealt, but it's also solved, as we saw in the beginning. So by utilizing different modalities of sensors. So for example, rain is no problem for radar, and if we have some radar sensor, we don't have any problems with rain, and which is usually problematic for either lidars or cameras and so on. And then by utilizing different sensors, we can have and sensor fusion, we can have also avoid this problem. I didn't mention here, maybe this would be also interesting for you. There are also some very nice like massive multi-agent simulators for the traffic. So for me, the focus is on the single kind of vehicle, but there are really some nice simulations like Sumo and also Carla now with some kind of very good visualization and so on, which are really interesting maybe for people who want to deal with some kind of multi-agent massive multi-agent problems.